Hi, I'm Xu Haichen. Presenting better CMOS produces clearer images. Learning space variant blur estimation for blend image superresolution. Blend image superresolution aims to reconstruct high-resolution images from low-resolution images with unknown degradations, such as blur. Most previous methods assume that blur is space invariant. However, in reality, it can be space variant. In this work, we firstly introduced two new datasets with space-variant blur to support further researches. Based on the datasets, we incorporate semantic information and design a novel cross-model fusion network, namely CMOS, that estimate both blur and semantics simultaneously. Then, the blur and semantics are used as prior knowledge and input into a non-blend image superresolution network to get final results. As a preliminary exploration, we built two datasets that contain out-of-focus blur, as it is one of the most common space-variant blur in real-life situations. Out-of-focus is caused by differences in depth. Every point that is not in the plane of focus corresponds to a circle of confusion in the image plane. The blur can be simulated by isotropic Gaussian kernels with standard deviation sigma related to the diameters of the circles of confusion. We employ the method proposed in Paper 1 to blur the images, and the ground truth blur map is constructed by sigma of each pixel. We choose NYU V2 and Cityscapes as original datasets. 1/4 of the images is blurred by space-invariant kernels, so that the models trained on the datasets are not limited by the space-variant situations. We refer to the datasets as NYU V2-BSR and Cityscapes-BSR, where BSR stands for Blend Image Superresolution. In the process of image superresolution, we have two motivations for incorporating semantics. According to reference 2, semantics is beneficial to recover finer image details. Besides, we observe that the sharp semantic edges are usually aligned with out-of-focus blur boundaries, and it can help to distinguish different blur amounts. As a result, we design a novel cross-model fusion network, CMOS, and a feature grouping interaction attention module, GIA, to estimate and leverage semantics. Specifically, GIA has two parallel streams to effectively interact features in both spatial and channel dimensions. Besides, it includes an upsample module to support inputs with different resolutions. CMOS is a multi-scale network with 3 stages. In the first stage, a fully convolutional encoder capable of generating multi-scale features is used to extract deep features. In the next stage, we employ task-specific heads to individually extract features for blur and semantics, and use GIA modules to facilitate interaction between these two modalities. In the last stage, a shorter path is created for each scale to the supervision using the GIA modules, and the results from all scales are combined to obtain final outcome. We use the mean absolute error for blur estimation and the cross-entropy loss for semantic segmentation. Please refer to our paper for more details. Qualitative and quantitative results on the newly introduced datasets NYU V2-BSR and Cityscapes-BSR demonstrate that our method surpasses other approaches, achieving state-of-the-art performance. The ablation study conducted on the GIA module provide evidence of its rational design and effectiveness. To demonstrate the effectiveness of incorporating semantics, we conduct an experiment where we remove semantics from the entire process. As seen from the table, the removal results in a decrease of 1.28 in peak signal-to-noise ratio, and a decrease of 0.002 in structural similarity. It highlights the significant impact and contribution of semantic information in enhancing the performance of our approach. Comparative experiments conducted on real-world images further substantiate the superiority of our method. Thank you for your attention. We will see you on Tuesday morning poster session with more details.